In a situation where we have a light source that's in a medium with a refractive index that's greater than a refractive index at another boundary, some interesting things start to occur. So let's look at the angle that the light ray makes with the surface. At a somewhat shallow angle, we get refraction as we always expect. And we have a little bit of reflection back into the material. As we make the angle greater, we get more refraction and we get reflected light. There's a certain point, though, at which the angle causes the light to go skim along the boundary. In other words, the angle on the side of medium 2 is at 90 degrees. Anything greater than that angle will cause total reflection back into medium 1. There will be no refraction. And this is total internal reflection. Now we can use Snell's law to figure this out. We have N1 sine theta 1 is equal to N2 sine, but if I want to know the critical angle, that sine is going to be 90 degrees. And sine of 90 degrees is 1, so I'm going to have the sine of theta 1 is equal to N2 over N1, and this N2 over N1, because N1 is greater than N2, is going to be less than 1, which I need for the arc sine. So theta 1 is equal to the arc sine of N2 divided by N1. When theta 1 is greater than that, I'm going to have total internal reflection. Now we can use this idea for different applications. One would be binoculars. You have these total internal reflections based on how these crystals are shaped and their refractive index to guide light from the eyepiece, or from the view lenses to the eyepieces. In the case of fiber optics, you get total internal reflection based on these refractive indexes, and because of the total internal reflection, very little light gets out of fiber optics, which makes it a fairly good medium to transmit information from point A to point B.